On a crisp spring morning at Aberdeen Proving Ground in Maryland, May the 12th, 1942, 5 different anti-tank systems lined up for a test that would change everything. The mist still clung to the range as the challenge was set. Hit a moving German Panzer III at 100 yards. This wasn't practice anymore. This was survival. Across North Africa, American paratroopers were getting torn apart by enemy armor. Their rifles couldn't do a thing against 25 tons of rolling steel. The situation had become desperate, and the stakes had never been higher. First to fire was the British Piat, a spigot mortar design carrying 32 pounds of what everyone called cutting-edge engineering. Months of development, backing from military contractors, official confidence. Then came the American rifle grenade, months of work by the best minds the Ordnance Department could gather. 3 more designs followed, each one representing what conventional military wisdom said would work. Then a young officer walked forward. 24 years old, Lieutenant Edward Ull, carrying what looked like someone had welded together a drain pipe with some wire coat hangers and a homemade trigger. The Weapons Review Board had already rejected this thing outright. Impractical, they'd said, too risky, no soldier should carry it. Ull's crude launcher fired 5 times that morning, 5 direct hits. Perfect accuracy. An improvised weapon made from scrap material that cost almost nothing to manufacture. Within days, General Marshall would order 5,000 units produced. By the time the war ended, this rejected weapon would transform lightly armed paratroopers into tank killers that German panzer crews learned to fear and respect. But first, a young engineer had to prove that the best ideas sometimes come from the most unexpected places. Colonel Leslie Skinner's office in the Ordnance Department that spring felt more like a tomb than a command center. He spread out the latest reports across his mahogany desk, and they all told the same grim story. In Libya, Rommel's Africa Corps was cutting through British forces like they weren't even there. American observers embedded with Commonwealth units kept sending back field reports that read like horror stories. The numbers didn't lie, and they didn't comfort either. A German Panzer III weighed 25 tons and could move across open desert at 25 miles per hour. An American paratrooper, loaded down with combat gear, carried 80 pounds and could sprint maybe 8 miles per hour on good ground if he had the strength left. When physics put those 2 things on a collision course, physics always won. And physics favored the Germans. Skinner pulled out a photograph from the Gazala line. British paratroopers had been dropped behind German positions to cut supply lines and disrupt operations. The mission had collapsed completely when Rommel's panzers rolled through their defensive positions like they were nothing. The boy's anti-tank rifle, a precision piece of British engineering weighing 39 pounds, proved completely worthless. Its half-inch rounds bounced off German armor like pebbles thrown at a ship. Out of 240 paratroopers who dropped that day, only 37 made it back to Allied territory. The production charts hanging on Skinner's office walls offered no hope at all. German factories were making tanks faster than America could build them. The Wehrmacht had learned combined arms warfare in Poland and France, perfecting how armor, infantry, and air support worked together as one machine. American forces, meanwhile, still relied on World War I tactics and equipment that had been outdated for 2 decades. But sitting on Skinner's desk was something that offered real promise. An idea that might actually work if anyone could figure out how to deliver it properly. The M10 shape charge grenade was a genuine breakthrough. A Swiss inventor named Henry Mohaupt had created a hollow charge design that could focus an explosive blast into a narrow jet of molten copper, punching straight through 50 millimeters of steel armor. Laboratory tests showed this warhead could penetrate any German tank currently in production. Every last one of them. The delivery problem, though, seemed impossible to solve. At 3.5 pounds, the M10 was too heavy to throw accurately. Rifle-launched versions destroyed the weapons firing them. The only way to actually use it required infantry to get close enough to touch enemy tanks, a suicide mission that no reasonable commander would ever order. Lieutenant Edward Ull showed up at Skinner's office on a Tuesday morning, fresh out of Lehigh University's mechanical engineering program and trying hard not to look overwhelmed by his first real assignment. At 24, he had the kind of careful, persistent thinking that engineering professors loved, though military bureaucrats usually found it irritating. His habit of sketching mechanical ideas on whatever surface was nearby had already earned disapproving looks from senior officers. Skinner handed him the M10 specifications and a thick stack of failed proposals. "What we need," the colonel explained, "is a way to get this warhead onto German armor from 300 yards out without killing our own people. Every solution we've tried either doesn't reach far enough or creates too much danger to the operator." Uhl spent 2 weeks working through the problem from every possible direction. Rifle-launched versions generated recoil that shattered weapon stocks and dislocated shoulders. Mortar-delivered rockets became wildly inaccurate past 50 yards. Spring-loaded catapults looked ridiculous and performed worse than they looked. Every potential answer created new problems that just kept multiplying. The real breakthrough came during a routine trip to Indian Head Naval Proving Ground in Maryland. Walking past the equipment disposal area, Uhl spotted a discarded 60mm mortar tube. 5 feet of steel pipe with exactly the right internal diameter to hold the M10 grenade. The inspiration hit him like lightning. Traditional rocket launchers failed because they tried to contain the whole combustion process inside complex machinery. But what if the rocket motor burned out completely before the projectile even left the launch tube? The operator would be protected by the tube itself, eliminating the back-blast danger entirely. The rocket would emerge with enough velocity to stay accurate at longer distances. Working in a borrowed machine shop, Uhl welded a pistol grip and simple electrical trigger to the mortar tube. He rigged up a battery system using standard cells and built basic iron sights from scrap metal. The first test, firing into the Potomac River, went better than he'd hoped. The rocket flew straight and true, while the launcher stayed intact and manageable. When Uhl showed his prototype to the Ordnance Review Board, the reaction was ice cold. Expert after expert tore into the design. "Too dangerous to carry into battle," said the small arms specialist. "The backblast will burn anyone standing behind the operator." The armor expert worried about rocket reliability. "Solid fuel motors are unpredictable," he insisted. "Half your rounds will probably misfire or blow up prematurely." The committee's decision came quickly. Stick with the proven British Spigot mortar technology. If the British wanted to risk their soldiers on experimental rocket launchers, that was their choice. But as summer approached, intelligence reports brought urgent news. German reconnaissance units had captured British special operations equipment, including prototype rocket launcher designs. Within weeks, Wehrmacht engineers were copying those concepts, racing to develop their own versions. The technological advantage that shape-charge warheads represented wouldn't stay American for long, not unless the United States could field a practical delivery system first. Aberdeen Proving Ground was chosen for the final test, set for May. 5 established anti-tank weapons would go head-to-head against Uhl's improvised launcher. Whoever won would get immediate production contracts. The losers would be forgotten. Uhl had one chance to prove that conventional wisdom could be dead wrong, that elegant simplicity might beat complex engineering, that a 24-year-old officer with a modified mortar tube could transform infantry warfare. The German panzers rolling across North Africa wouldn't wait for military committees to make up their minds. Uhl worked 18-hour days in Skinner's workshop, turning his crude prototype into something worthy of mass production. The original mortar tube needed serious reinforcement to survive repeated firings. He wrapped the entire length with steel piano wire, creating a secondary containment system that would prevent total failure even if the primary tube cracked under pressure. The electrical trigger system had to be reliable. He wired 2 diesel batteries in parallel to ensure firing would work, even if one power source failed in actual combat. The shoulder stock created its own engineering puzzle. Early test firings generated enough recoil to bruise operators' shoulders and ruin their aim. Uhl carved a new stock from solid walnut, orienting the grain to absorb impact while staying stable against the shooter's body. The wood's natural shock absorption worked better than steel options that just transmitted every vibration straight to the person firing. The rocket itself was where Uhl showed real engineering brilliance. He joined the M10's proven shape-charge warhead to a solid propellant motor that would burn completely inside the 54-inch launch tube. Getting the propellant grain right was everything. Burn too fast and the launcher would explode. Burn too slow and unburned fuel would endanger the operator. After dozens of static tests, all hit the perfect balance. Complete combustion in 1/50 of a second, accelerating the projectile to 265 feet per second. The technical specifications that came out of this work would define infantry anti-tank combat for generations. Total launcher weight, 13 pounds. Each rocket added 3.4 pounds. Effective range reached 300 yards with reasonable accuracy. Armor penetration capability covered 4 inches of homogeneous steel plate, enough to defeat any German tank side or rear armor. Rate of fire hit 6 rounds per minute with a trained 2-man crew, assuming ammunition supply. Aberdeen proving ground filled with unusual activity as the competing weapon systems arrived for evaluation. The British Piat came with impressive credentials developed by Special Operations Executive, field-tested by commandos, carrying endorsement from Churchill's technical advisors. At 32 pounds, this weapon demanded extraordinary strength just to operate it. The shooter had to wrestle with the powerful spring mechanism, cock it, and hold steady while aiming. The hollow charge projectile could theoretically bore through German armor, but only if the operator could manage the unwieldy device while keeping targets in sight. The American M10 rifle grenade represented a modest step forward from what already existed. Standard infantry rifles could fire these shaped charge warheads using blank cartridges, giving theoretically every soldier anti-tank capability. Yet combat experience from North Africa told a different story. Reports showed serious problems. The range fell short, accuracy was unreliable, and the warheads themselves often failed to function. When infantry faced tanks, they had almost nothing to defend themselves with. 3 established defense contractors submitted experimental designs for evaluation. Each represented serious engineering effort backed by millions in research funding and decades of corporate knowledge. Their fire control systems promised better accuracy. Their advanced materials meant less weight while keeping strength intact. Their propellant formulations claimed they'd work in extreme conditions. UL's launcher, by contrast, looked crude. No sophisticated systems, no exotic materials, no complicated calculations needed. Just a steel tube with a grip, a trigger, and simple iron sights that any soldier could instantly understand. That very simplicity made experts doubt it. They'd learned to associate complexity with capability. The testing at Aberdeen would be demanding but fair. Each weapon would fire at a moving German Panzer III traveling at 15 miles per hour, exactly the range and speed encountered in actual combat. The target would cross at 100 yards out. Every system got 5 attempts to prove accuracy and reliability. May 12th dawned clear and calm, perfect conditions for testing. UL arrived early only to find disaster. His launcher's sights had been damaged in transport. The carefully machined iron sights lay twisted and broken in their carrying case, the result of careless handling by Aberdeen's logistics crew. With only hours before the demonstration, panic nearly took over. Skinner found him trying desperately to repair them with whatever tools he had available. "We need sights that work," the colonel said plainly, "not sights that look pretty." Working quickly together, they improvised replacement aiming devices. A straightened wire coat hanger and a nail from the workshop floor became their solution. The result looked absurd, twisted metal held together with electrical tape, but it provided the basic alignment needed to acquire targets. The crowd gathering for the demonstration included the highest levels of military procurement. Major General Gaillard Barnes, Chief of Research and Engineering for Army Ordnance, would decide which weapon entered production. British intelligence observers watched carefully, evaluating American capabilities while protecting their own secrets. Defense contractor executives stood nervously as months of design work and millions in investment faced practical evaluation. The pressure extended beyond procurement decisions. German forces were advancing through North Africa, while American infantry remained poorly equipped for modern warfare. Every day's delay meant more casualties, more lost ground, more proof that Allied forces couldn't match German capabilities. The winning weapon would immediately go into mass production, potentially shifting the war's trajectory in theaters where armor dominated. Ull checked his improvised sights one last time, feeling the launcher's familiar weight settle across his shoulder. The coat hanger device looked ridiculous, but it gave the basic alignment necessary for accurate shooting. More importantly, the weapon's core simplicity stayed unchanged. Point the tube, pull the trigger, watch the rocket fly straight. No complicated calculations, no finicky adjustments, no complex mechanisms prone to failing under combat stress. This test would show whether elegant simplicity could beat institutional complexity, whether a young engineer's unconventional approach could solve problems that had defeated military experts, whether American infantry would finally get weapons that could stop German tanks. 5 shots would determine anti-tank warfare's future. The British Piat fired first, handled by a team of Royal Engineers trained extensively at Woolwich Arsenal. The 32-pound launcher required both men to manage its complex spring loading, one holding steady while the other cocked the powerful steel spring that would propel the charge. The Panzer III began its traverse at exactly 15 miles per hour, its distinctive grey camouflage pattern stark against the Maryland landscape. The first Piat round launched with a distinctive thump as the spring released its stored energy violently. The projectile arced through the morning air on a promising ballistic path for the first 200 yards. But as the shaped charge bomb approached the moving target, wind drift revealed the inherent inaccuracy of the Spigot mortar system. The round hit 15 yards short, sending up dirt and debris that momentarily hid the target vehicle. 4 more attempts produced similar failures. The spring mechanism proved difficult to cock under pressure, needing nearly 30 seconds between shots while the target kept moving relentlessly. 1 round flew high over the turret entirely. Another struck ground 20 yards left, showing how sensitive the weapon was to operator technique. The final 2 shots came closer, but still missed by margins that would be fatal in real combat. The American rifle grenade team stepped forward with confident professionalism. Their M1 Garands fitted with special launching attachments and blank cartridges. This system offered theoretical advantages. Every rifleman could become an anti-tank gunner, and the familiar weapon platform needed minimal additional training. The team leader, a veteran sergeant from Fort Benning's infantry school, had personally supervised hundreds of training exercises with the M10 warhead. The first shot launched cleanly, the blank cartridge providing adequate thrust to send the shaped charge grenade toward the moving target. But fundamental limitations of rifle launch systems immediately appeared. The grenade's ballistic properties weren't suited for accurate long-range engagement, following an unpredictable flight path that defied precise aiming. The round landed short and left, its shaped charge detonating harmlessly in sand. Subsequent attempts revealed additional failures. The rifle's wooden stock cracked under the stress of repeated launching. Its construction proved inadequate for the forces generated by the heavy projectile. The sergeant's shoulder showed visible bruising after 3 shots, affecting his ability to maintain steady aim. The final 2 grenades landed closer to the target, but still outside the lethal radius needed for effective armor penetration. The 3 experimental designs from established defense contractors delivered similarly disappointing results. Each showed sophisticated engineering and careful attention to theoretical requirements, but none could consistently hit a moving target under realistic conditions. Complex sighting systems proved fragile and hard to operate under pressure. Advanced materials failed to deliver promised improvements. Specialized technologies that worked perfectly in laboratories struggled with the chaos of actual weapons testing. By noon, the scorecard was devastating. Established anti-tank weapons 0, moving Panzer III 5. Every expert-approved system had failed to demonstrate basic capability for infantry anti-tank operations. Watching officials began murmuring among themselves, discussing the implications of American forces entering combat without effective armor-defeating weapons. General Barnes called for a lunch break, though his expression suggested appetite was the last thing on his mind. British intelligence representatives huddled quietly, undoubtedly drafting reports that would reach London within hours. Defense contractor executives looked increasingly uncomfortable as their sophisticated systems lay silent on the range, defeated by the simple challenge of hitting a moving target. Ull spent the break checking his improvised launcher one final time. The coat hanger sights looked even more ridiculous in daylight, their twisted metal construction contrasting sharply with the precision optics that had failed throughout the morning. But the weapon's fundamental mechanics remained sound. The steel tube was properly reinforced, the electrical system showed full battery charge. The rocket motors had been carefully inspected for defects. When General Barnes called for the final demonstration, Ull walked to the firing line with quiet confidence. The familiar weight of the launcher settled naturally across his shoulder, its balance point perfect for stable shooting. The improvised sights provided basic reference points that aligned intuitively with his natural aiming instincts. The Panzer III began its traverse for the 6th time that day, its engine noise clearly audible across the range. Ull tracked the target through his coat hanger sights, waiting for the optimal moment when target movement, wind conditions, and rocket flight time would intersect perfectly. His finger found the electrical trigger, feeling the familiar resistance that preceded ignition. The first rocket launched with a sharp crack, its solid fuel motor burning completely within the tube before the projectile emerged. The shaped charge warhead flew straight and true, following a flat trajectory that contrasted dramatically with the arcing flights of previous weapons. Impact came precisely where Ull had aimed, center mass on the Panzer's hull. The hollow charge warhead detonated with devastating effect, punching a clean hole through 50 millimeters of armor plate. The watching crowd fell silent. One successful shot proved nothing. Lucky hits occurred even with inadequate weapons. But Ull was already loading his second rocket, his movements smooth and practiced from weeks of preparation. The Panzer continued its mechanical traverse, presenting a fresh target angle as it moved across the range. The second shot struck the turret with identical precision, penetrating armor that would have protected the crew compartment in actual combat. The third rocket hit exactly where aimed. The fourth found its mark with mathematical certainty. The fifth and final shot struck center mass, completing a perfect demonstration of accuracy that left no room for doubt or interpretation. The scorecard now read, Ull's improvised rocket launcher 5 hits, moving Panzer 0. The afternoon sun beat down on the firing range as General Barnes made his way toward the weapon emplacement. His face remained carefully neutral, betraying nothing of what he was thinking. He reached for the launcher, gauging its heft in his hands, then studied the improvised coat hanger sighting mechanism that had proven itself accurate shot after shot. His movements carried the confidence of a man who had spent his entire career personally testing weapon systems. He raised the launcher to his shoulder, feeling how the weight distributed along his frame, assessing the balance with the methodical precision of someone who had evaluated hundreds of firearms and munitions throughout a long military career. The launcher felt substantially lighter than the Piat, far more manageable than the cumbersome rifles that required special grenade attachments. He sighted through the makeshift aiming device, impressed by how smoothly the weapon aligned with distant targets. "You know," Barnes said with a slight smile, "that really does remind me of the bazooka from the Bob Burns show on the radio." He was referring to the comedian's musical novelty, constructed from 2 lengths of gas pipe fitted together with a whiskey funnel as the bell. The observation drew knowing laughter from the officers gathered around, though Barnes spoke with genuine respect rather than ridicule. The nickname seemed to capture something true about the weapon's essential character. Here was a tool built for practical results, not for appearance or elaborate engineering. Barnes proceeded to load the rocket and fire multiple rounds at targets arranged across the test range. Each shot performed flawlessly, exactly as the demonstration had shown. The ignition ignited cleanly, the flight path stayed true, and the warhead delivered exactly the destructive power needed against armored vehicles. The shaped charge detonations punched through steel with brutal efficiency, creating apertures that would have spelled instant death for tank crews in genuine combat situations. Equally important was how straightforward the weapon proved to operate. Any reasonably trained infantryman could master this system with just a handful of hours of instruction. "How quickly can we get 5,000 of these in the field?" Barnes demanded, his voice carrying the weight of command decision. The question landed like a thunderbolt. Ulz felt his pulse accelerate, his thoughts suddenly scattered by the velocity of this moment. What had started as a successful test was instantly transforming into something far larger, and his mind struggled to keep pace with the implications unfolding before him. "Sir, Ulz stammered, not entirely certain he had heard correctly. "General Electric receives the contract," Barnes stated without hesitation, his mind already settled on the course ahead. 30 days until the first units leave the factory. "We're calling it the 2.36-inch rocket launcher M1, though I suspect every soldier who carries one will have a different name in mind." The Bridgeport facility of General Electric suddenly became a cauldron of industrial intensity the company had not experienced since the previous World War. Engineers who had devoted their careers to designing electrical systems and household items abruptly found themselves racing to produce anti-tank weapons destined for a global conflict. Moving from working prototype to factory production floor exposed complications that the laboratory had never revealed. Managing quality proved to be the central obstacle. The initial production run turned out defective weapons that would have meant death in actual combat scenarios. The steel tubes sourced from various suppliers possessed different metallurgical characteristics. Some batches simply could not withstand the repeated stress of firing rockets. The firing systems misfunctioned with disturbing regularity, leaving soldiers holding weapons that simply would not discharge when German tanks came into view. The M6 rocket itself created even greater difficulties. The propellant grains fractured throughout transport, resulting in erratic combustion that sent rockets careening wildly off their intended path. Atmospheric moisture corroded the electrical components, preventing ignition even when the launcher functioned properly. Temperature swings during storage degraded the warheads, sometimes triggering accidental detonations that killed the operators instead of destroying enemy vehicles. October 1942 brought devastating reports from North Africa. American soldiers had received virtually no instruction in this entirely new weapon system, simply treating it as standard equipment rather than a sophisticated apparatus demanding specialized training. The rockets proved so unreliable in the harsh desert environment that the hit rate fell below 20%, even on stationary objectives. Colonel James Powell filed a devastating report from Kasserine Pass. "The bazooka has demonstrated severe limitations in actual battlefield conditions. During combat engagements, troops fired 47 rockets at German armor, with only 3 reaching their targets, and not one confirmed tank destruction resulted. Immediate withdrawal of this system is recommended until fundamental design changes are implemented." Yet within the tide of negative assessments, one military organization perceived possibilities others had overlooked. American airborne forces confronted an entirely different tactical situation than conventional ground troops. Paratroopers dropped behind enemy positions, carried nothing but what fitted on their bodies, fighting isolated without access to heavy weapons, artillery, or reliable resupply lines. Conventional anti-tank guns were simply too heavy for airborne operations. The British rifle weighed nearly 40 pounds. The American 37mm anti-tank cannon required a vehicle and several crew members to operate. The bazooka offered something genuinely revolutionary: legitimate anti-tank power in a package light enough for individual soldiers to transport. At 13 pounds, paratroopers already encumbered with parachutes, radios, ammunition, and survival gear could manage the launcher. The shaped charge warheads possessed sufficient penetrating power to punch through German tanks if operators struck vulnerable areas on the side or rear. In November 1942, General Matthew Ridgway, commanding the 82nd Airborne Division, submitted an official request for a modified version. Create a bazooka variant specifically suited to paratrooper requirements. The standard 54-inch launcher simply would not fit inside transport aircraft, where space requirements demanded every item serve multiple roles efficiently. Ulz returned to his workshop, confronting an engineering problem that seemed nearly insurmountable. Paratroopers required the anti-tank capability the bazooka offered, yet they needed a package that could be transported during jumps without fouling parachute lines or creating protruding parts that might snag on aircraft elements. Maintaining the original ballistic performance while dramatically shrinking the physical dimensions represented the central challenge. The solution arrived through ingenious mechanical design. Ulls created the M9 airborne version with the capability to split into two 31-inch sections connected by a threaded joining mechanism. Paratroopers could strap the components directly to their bodies during insertion, then reassemble them into a complete weapon in roughly 30 seconds after hitting the ground. This separation system added negligible weight while addressing the core transport problem. Yet Ulls expanded his improvements considerably beyond this basic modification. The M9 incorporated an extended tube stretching 61 inches when assembled compared to the original 54 inches, enhancing accuracy through prolonged rocket acceleration. An improved magneto-ignition system eliminated the battery failures that had devastated earlier production runs. Steel components replaced wooden ones throughout, cutting weight while dramatically improving durability under harsh operational conditions. The new M6A3 rocket incorporated everything learned from catastrophic field experiences. The redesigned warhead featured a blunt configuration that maximized shape charge performance, increasing penetration capability from 3 inches to 4 inches through homogeneous steel. Enhanced burn characteristics generated higher velocity and straighter flight, dramatically improving accuracy at the 350-yard effective range. By early 1943, the thoroughly redesigned system stood prepared for its ultimate evaluation in actual combat, with airborne formations preparing for European operations. The pre-dawn hours of June 6, 1944, brought the sound of 1,200 transport aircraft droning across the English Channel toward occupied France. Within the congested cargo holds of C-47 Skytrains, 20,000 American paratroopers performed final checks of their equipment before launching the largest airborne operation in military history. Secured alongside parachutes, ammunition, and survival kits, the M9 bazookas represented an innovative tactical capability that German commanders had never anticipated. Staff Sergeant Mike Ranney of the 2nd Battalion, 506th Parachute Infantry Regiment, felt the familiar pressure of his separated bazooka sections pressed against his ribs as his aircraft neared Drop Zone A near Sainte-Mère-Église. The 31-inch tubes had turned into muscle memory through intensive English training, but this moment would reveal whether Ulls's engineering could transform lightly equipped paratroopers into effective tank killers. The actual drop scattered American forces across the Norman landscape in patterns no planner had foreseen. Strong winds, hostile fire, and pilot error deposited paratroopers miles from intended zones, creating scattered groups of isolated men positioned deep within German defensive territory. For standard infantry formations, such dispersion spelled disaster. For airborne forces carrying portable anti-tank weapons, it created tactical opportunities that German defenders had never encountered. Ranney splashed down in a waterlogged field more than 2 miles from his designated zone, immediately assembling his launcher while German voices carried through the darkness. The threaded connection system functioned precisely as designed, converting 2 unwieldy tubes into an operational weapon in under 30 seconds. Nearby paratroopers performed identical assembly procedures, forming small detachments capable of engaging German armor without requiring support from conventional forces. The first genuine engagement erupted at dawn, near Sainte-Mère-Église, where German reserves launched a counter-offensive designed to push back toward the invasion beaches before Allied forces could solidify their lodgment. 3 or 4 Panzer IVs advanced down the road with supporting infantry and half-tracks, moving towards scattered 82nd Airborne positions. Traditional doctrine would have made lightly armed paratroopers helpless against such a force, forcing retreat or accepting annihilation. Instead, Sergeant Ranney and Private First Class Walter Gordon positioned themselves in a ditch approximately 30 yards from the roadway, their launcher armed with an M6A3 rocket. The enhanced warhead offered 4 inches of penetration, sufficient to breach the Panzer IV's 50mm side armor at the right angle. The first tank rolled past their position at walking speed, presenting a perfect flank shot that older anti-tank weapons could never have attempted. Ranney activated the magneto-ignition system, launching the rocket on a flat path that struck the tank's hull just behind the driver's compartment. The shape-charge warhead detonated catastrophically, tearing through armor and detonating internal ammunition storage. The tank lurched to a halt, smoke billowing from open hatches as surviving crew members scrambled free from the burning wreckage. The following Panzer IV attempted to navigate around its destroyed predecessor, but another bazooka team positioned among apple trees 50 yards away unleashed their rocket at its rear armor. Private James Alley's shot penetrated the engine compartment, rendering the tank immobile and stranding it in the road's center. The third German tank, recognizing the area bristled with anti-tank threats, reversed direction and withdrew toward coastal defensive positions. Within 3 hours of landing, American paratroopers had demonstrated a tactical capability that fundamentally transformed the Normandy campaign. German armor, previously immune to infantry assault, now faced lethal danger from soldiers appearing unexpectedly behind the lines. The psychological impact matched or exceeded the actual physical destruction. German tank crews approached any area possibly harboring American paratroopers with extreme wariness. The tactical transformation extended throughout the invasion sector. Near Carentan, a bazooka team under Lieutenant Richard Winters destroyed 3 German tanks in 10 minutes, shattering an armored counterattack threatening to cut the causeway linking Utah Beach inland. At Shepherd's Plank, paratroopers deployed bazookas against 2 Sturmgeschütze assault guns dominating approaches to a vital bridge. German reports captured later revealed the profound shift. Wehrmacht officers documented with alarm that American paratroopers no longer behaved like conventional light infantry, retreating from armor. Instead, they actively sought German tanks, utilizing superior mobility and terrain knowledge to execute devastating ambushes against mechanized forces. By late June, the tactical revolution became statistically evident. The 82nd and 101st Airborne Divisions had destroyed or disabled 47 German armored vehicles using bazookas, compared to 0 tank kills in prior campaigns. Combat effectiveness dramatically exceeded laboratory projections: 70% accuracy against stationary targets, 45% against moving tanks within 100 yards. The M6A3 rocket penetrated the side and rear armor of every German tank model, including the Tiger I, whose frontal protection resisted bazooka attack. More crucially, the psychological impact extended beyond actual destructive capacity. German panzer crews, who had confidently relied on technological superiority, now approached every engagement aware that death could strike from paratroopers they could not see. Each airborne company received 4 bazookas, while glider troops got 6 per unit, giving paratroopers anti-tank firepower equivalent to a conventional platoon, while preserving the mobility that defined airborne tactics. German commanders schooled in exploiting the traditional vulnerability of light infantry to armor discovered they faced an opponent that had erased their principal tactical advantage. Yet as the bazooka proved itself across Norman terrain, intelligence reached headquarters with troubling information from the eastern fighting. German engineers studying captured American weapons had developed their own shoulder-fired rocket, the Panzerschreck, mounting an 88mm warhead capable of penetrating 6 inches of armor. The student had begun to challenge the teacher, threatening to transform Ols's innovation into a liability for the forces it was designed to protect. The ongoing competition between offensive advancement and defensive innovation, between American ingenuity and German engineering prowess, was entering a dangerous new phase that would determine whether the bazooka retained its revolutionary advantage or became simply another obsolete weapon in warfare's perpetual technological cycle.